Hello and welcome. In this video, we will discuss few examples of DFA. Consider the language over alphabet set A, and that language accept the string A. So language is having only one string, that is A, and for this language we have to design deterministic finite automata. So from state Q0, if we read letter A, then we are moving to final state because A is a valid string. So when we read it from the initial state, it should be accepted. And no other string is part of language, so we don't have to derive any other transition from this. So this is the transition diagram for the given language. Equivalently, we can also draw a transition table for that. So this DFA contains two states. So there will be two rows in the table, and there is only one alphabet in sigma. So there will be one column for that alphabet symbol, input symbol A. So Q0, if we read A from it, then we are going to Q1. And from Q1, if we read A, then we are not going anywhere, right? So that's a 5, or we can say it's a dead state. And Q0 is initial state, so we will put arrow in front of it. Q1 is the final state, so we will denote it by star. We can also write down the transition function in form of delta function, like delta Q0 comma A. So from Q0, if we read A, we are moving to Q1, and from Q1, if we read A, then there is no transition, so it's a 5. And this is formal representation of the DFA. That is the 5-tuple representation. Q, sigma, delta, Q0, and F. So Q is a set of states. So here we have two states, Q0 comma Q1. Then sigma contains only one alphabet, that is A. Delta is the transition function, which is already discussed. Q0 is the Q0, that is the initial state, and Q1 is the final state. So that is shown in this D. Construct DFA over sigma is equal to A, which accepts string A and AA. So now language contains two strings A and AA. So if we read A from the initial state Q0, it should go to the final state, that is Q1. From Q1, if we read another A, then that should also be accepted because we have read out 2A, and 2A is a valid string. So we are moving to some state Q2, and that is also final state. Now from Q2 we cannot read anything, so there is no transition from the Q2 for any input. This is the transition table for that. This is the transition function for that, and this is the formal representation of the given DFA. Construct DFA over alphabet set A, which accepts all the strings over A. So any string that we can formulate using A, they all will be the part of language. So our language would be 1A, 2A, 3A, 4A, and infinite A. Any number of A's we can read. So if we read first A from Q0, it should be accepted because A is a part of language. We should always start with the minimal length string. So this is the minimal transition diagram. Now we will add appropriate arcs to generate rest of the strings. From Q0, one arc is already out. We can't do anything there. But from Q1, no output is going. So we can have one transition from Q1. And if I put self loop of A here, then we can read any number of A and still we will be in final state. So A is accepted, AA accepted, 3A accepted, 4A accepted, infinite A would be accepted. So this is the correct DFA for the given language. This is the transition table. This is the transition function for the same. And this is a formal representation of the DFA. Construct DFA over sigma is equal to A comma B. So now our language is defined over two alphabet symbols A and B, which accepts all the strings of length 2. So language is defined over two alphabet and the length of strings must be 2. So our L would be AA, AB, BA, and BB. This is the initial state. If we read first A or B, then it should go to the non-final state Q1 because A or B is not part of our language. But when we read second A or B, it should go to the final state Q2 because now we are reading two symbols, either AA, AB, BA, or BB. In any order we can read it. From Q2 we cannot read anything. If we read any symbol, we are going to the final state, in dead state. And in dead state, if we read any symbol, we will remain in dead state. So this is the transition diagram. Even if we do not show any transition out of Q2, that is fine. That states are not required to show explicitly. So we can skip that part as well. The transition diagram for the same, and these are the transition functions for the given DFA. Construct DFA over alphabet set A comma B, which accepts all the strings of length at least 2. So string length should be at least 2. So string could be of length more than 2 as well. Fine. So strings of length 2, 3, 4, 5 up to infinity. So epsilon is not accepted, which is string of length 0. A and B is also not accepted because they are strings of length 1. So our DFA, the minimum length DFA, minimum length string is AA, AB, BA, BB. So first we'll draw DFA for that, and then we will extend the arcs so that we can produce all remaining strings in the language. From Q0, if we read AB, we are in non-final state Q1. From Q1, if we read A or B, we are going to the final state Q2 because that will have 2 letters when we move from Q0 to Q2. So that is valid string. From Q2, we can read any combination of A and B. That will give me the strings of length 3, 4, 5, 6 up to infinity. So this is the desired DFA. And this is the transition table for the DFA. Construct DFA over sigma is equal to A comma B, which accepts all the strings of length at most 2. So string length cannot be more than 2. It could be 0, it could be 1, it could be 2. So string with length 0 is epsilon. Strings with length 1 are A and B, and strings with length 2 are AA, AB, BA and BB. All these are valid string. Any other string which is having length greater than 2 are not acceptable. So epsilon is accepted. Whenever epsilon is part of language, initial state would be the final state. Remember that. We must have to make initial state as a final, so that when we start, we are already in final state without reading anything. So Q0 is final state. If we read A or B, then also we are going to the final state. So that Q1 will also be final. See, we should not make AB as a self loop on state Q0. Otherwise, we can read string of any length. We can keep iterating through that self loop, and we can have accepted strings of length 2, 3, 4, 5, etc. And that is why we are moving to another state Q1 on reading AB. So Q1 will accept strings of length 1. And from Q1, if we read one more symbol, then we are going to Q2. And Q2 will accept all the strings of length 2. Now from Q2, there cannot be any further transition. Otherwise, it would be strings of length 3. So if we read anything, then we will be in dead state. Right? And from dead state, if we read A or B, we will remain in the same state. So this is the desired DFA, and this is corresponding transition table for that. So let us compare. This one is the DFA for string length exactly 2. So Q2 is the final state. This one is string length less than or equal to 2. So strings of length 0, 1 or 2 are accepted, and that is why Q0, Q1 and Q2 are final state. And this is the DFA for string length greater than or equal to 2. So after accepting 2 symbols, we have a self loop, and that can create strings of any length 3, 4, 5 or whatever. Design finite automata for the strings whose length mode 2 is 0. That means our automata should accept only those strings whose length is even, because the mode of even number with 2 will be always 0. 0 mode 2 is 0, 2 mode 2 is 0, 4 mode 2 is 0, 6 mode 2 is 0. And if we take mode of even number with 2, then that would be 1. Right? So the language would be strings of length 0, strings with length 2, strings with length 4, 6 and etc. So this is what the some of the strings in length in language L. As epsilon is part of language, initial state must be final state. Then only it will accept the epsilon. Now when we read one symbol, it's a string of length odd. So we are moving to some non-final state Q1 because A and B are not acceptable. So we cannot remain in final state. So Q1 is not acceptable state. When we read second symbol, it becomes even length string, because from Q0 we are reading one symbol and we are going to Q1. From Q1 we are reading another symbol, second symbol, so it becomes even length string, so it should be accepted. When we read third symbol from Q0, the string becomes of length odd, so it goes to Q1. From Q1, if we read fourth symbol, it becomes even. So we are coming back to Q0. That is accepted. So this DFA will simulate all the strings of length even. Let us simulate it. Consider W is equal to B double AB. So length of W mod 2 is equal to 0 here, as we can see. So initially we are in state Q0 and our string is B double AB. If we look at for configuration Q0 comma B, then reading B from Q0 we are moving to state Q1. So we are in Q1 and the remaining string is AAB. From Q1, if we read A, then we are moving back to Q0 and our remaining string is AB. From Q0, if we read A, it is going to Q1 and remaining string is B. From Q1, if we read B, then it is going to Q0 and no character is left. That means epsilon is left. So whenever there is epsilon and the current state is final state, then we can say that that particular string is accepted by the FA. So here as we can see that we are in state Q0, entire string is processed and Q0 is a final state and hence BAAB is accepted because it is a even length string. Let us try it for some odd length string. So here W is having 7 letters. It's a odd. Let us check whether it will be accepted by this or not. So initial configuration would be Q0, comma our string. So first letter is A. So on reading A from Q0, we are moving to Q1. From Q1, if we read A, then we are moving to Q0. Remaining string is ABA double B. From Q0, if we read A, we are moving to Q1. Remaining string is BA double B. From Q1, when we read B, we are going to Q0. From Q0, if we read A, we are moving to Q1. From Q1, if we read B, it's going to Q0. And from Q0, if we read B, we are moving to Q1. And no characters is left into the string. It's a epsilon. It's a null. So when string is scanned, we are in state Q1. Q1 is not final state and hence this string is rejected. And obviously it should be because this DFA is for even length string. And right now we are trying to parse odd length string. So it will reject that this is not a valid string. Design finite automata for strings such that length of string mode 2 is even. It means we are now drawing DFA for the odd length strings because odd number mode 2 would be always 1. So our language would be of strings A, B, that is the strings of length 1, then AAA, AAB, ABA, ABB, etc. strings of length 3, then strings of length 5, etc. Initially, we will derive DFA for the minimum length string that is A, comma B, and then we will extend it. Epsilon is not part of language, so initial state cannot be final state. So initial state is just a Q0, and when we read A or B, it's an odd length string, so it should be accepted, and that is why Q1 is a final state. When we read second symbol from Q1, it will become even. It means we should go back to the Q0 because it is odd length, even length string. From Q0, if we read third symbol, then it becomes odd length string, so it is accepted. From Q1, if we read fourth symbol, then it becomes even length string, so it goes to the non-final state. So through this DFA, we can generate any string of length odd. And this is the proof we just saw on previous slide. So odd even length string would be rejected and odd length string would be accepted. Design finite automata such that string length mode 3 is equal to 0. It means automata would only accept the strings whose length is multiple of 3. So strings of length 0, strings of length 3, strings of length 6, strings of length 9 will be accepted. Combination of A and B could be anything, but length would be either 0 or 3 or 6 or 9, etc. As epsilon is the part of language, initial state would be the final state. And when we read one symbol, it's not multiple of 3. So we are in another some state, non-final state Q1. If we read second symbol, again we are in some non-final state Q2. And when we read third symbol, it's a multiple of 3. So we are in Q0. For fourth symbol, we are in Q1. For fifth symbol, we are in Q2. For sixth symbol, we will be in Q0 because 6 is multiple of 3. So you see that this DFA will simulate all the strings of length of multiple 3. Right? So epsilon, then strings of length 3, 6, 9, etc. It will accept, and all remaining length strings of length 1, 2, 4, 5, 7, 8, etc. all will be rejected. There is a simplification of this. Whenever we want to compute or we want to derive DFA for the language like the string length mode n is equal to some k, it requires n states. That is the one fact. Okay, this k could be anything, 0, 1, 2, 3, whatever. So that might be length of string mode n is equal to 0, or it may be 1, or it may be 2, etc. But ultimately it requires n states. K could take any value. The another observation, we can also write the string length mode n is equal to k, or we can say w mode n congruent to k. So that we represent in this way. Okay. Again, both representations are same. If we write w mode n is equal to k, or we write w mode n congruent to k, they have a same meaning. And in this case, we have to make qk state as a final state. So two things are fixed. Whenever we have to design DFA for some length mode n is equal to k, then it will take n states, and the kth state we have to make as a final state. Let us try to understand with the example. So here w mode 3 is 0. Length w mode 3 is 0. So here n is equal to 3. So it will take 3 states, q0, q1, q2. And k is equal to 0. So qk, that means q0 state would be the final state. If I want to derive the DFA for length w mode 3 is equal to 1, then here n is 3. So there will be 3 states, q0, q1, q2. And k is equal to 1. So qk, that is q1 state, would become the final state. And string length mode 3 is equal to 2. Here n is 3, k is 2. So q2 state would be the final state. So this two rules will help us a lot in designing such complicated DFAs. Design minimal DFA for string belongs to a comma b whole star such that number of a in string w should be exactly 2. So a string is over alphabet a comma b. We can have any length string. Just the condition is that number of a in each string should be exactly 2, not less, not more. There is no restriction on b. B can be anything. So we can have minimum length string as a double a. Then we can have a string of length 3, that is b double a, aba, double ab. Then we can have a strings of length 4, 5, etc. And you see that in all strings we have exactly 2a. So to draw DFA for this, first we'll draw DFA for the minimum length string, that is aa, and we are done. So this will accept only aa string. Now we will adjust the arcs of b such that it will produce all the strings in L. Whenever we have to add the arc, we should always try to create arc with minimum length. So first we should evaluate if self loop is possible or not. If it is not possible, then we should try to connect it with next state, whether it is possible or not. If it is not possible, then we'll check for the next to next or previous to previous state in that way. So from Q0, transition of A is already out, transition of B is missing. Can we have self loop of B here? If we put the self loop and if it is creating all valid string, then we will keep it. Otherwise, we will create arc from Q0 to Q1 for B. So if we put arc of, okay, before that, if we read third A, then it is going to be dead state, right? Because a string can have exactly 2A, not more than 2. Okay. If we read any number of B's from Q0, then also to go to the final state, we must have to read 2A. So these all strings will be valid. Double A is valid, B double A is valid, double B double A, triple B double A, 4B double A, any number of B's followed by double A is valid. Clear? So this self loop is valid. So let's keep it as a self loop. From Q1, transition of A is out, transition of B is remaining. Can we put the transition of B as a self loop? If we do that, and then we can have a double A, then A, B, A double B, A triple B, A 4 B, A, all strings are valid because they already have exactly 2 A's into every string. So this is also valid arc. Same way, from Q2, we can have an arc of B as a self loop. So after reading 2A, we can have any number of B's. So this is the valid DFA. This is how we have to build it step by step. First, you design it for the smallest possible string and then try to adjust the arc. Design minimal DFA for all the strings W defined over alphabet set A comma B such that number of A in string W mode 2 is equal to 0 Or we can also say that number of A in string W mode 2 congruent to 0. Right? Two definitions we have discussed on previous slide. Okay, so first we need to understand which are the strings in which number of A mode 2 is 0. So there could be 0A, there could be 2A, there could be 4A, 6A. So there should be even number of A's. Right? 0A, restriction is not there on B. B can be anything. It can be 1B, 0B, 2B, 5B, any number of B's. And it could appear before A, it could appear between A, it could appear at the end of A, anything is possible. But number of A should be even. Epsilon is part of language. So initial state would be the final state. When we read first A, it should go to the non-final state. And when we read another A, it comes to the final state because we have read out even number of A. So this DFA will simulate the strings of even length, even number of A's. 1A not accepted, 2 accepted, 3 not accepted, 4 accepted, 5 not accepted, 6 accepted, etc. So a 50% task is done that all the strings of even length of A are accepted. So NA, number of A's in strings are always even. But B's are not present. So we have to now introduce the arc of B. From Q0, can we have self-loop of B? Yes, obviously we can read any number of B's. Fine. Then we are reading A and again reading second A, then only we are coming to Q0. So before A we can have any number of B's. After A we can have any number of B's. But to go to the final state, we must have to read even number of B, then only it is accepted. So this is the desired DFA. Design minimal DFA for strings over alphabet A, B such that number of A in string mode 3 is 0. So number of A should be multiple of 3 now. Or the another representation is what? Number of A in string W mode 3 congruent to 0. In either way we can speak it. So it will contain all the strings in which number of A's are multiple of 3. So there would be 0A, 3A, 6A, 9A, etc. And there is no restriction on number of B's. So as epsilon is part of language, initial state would be the final state. When we read 1A or 2A, we will be in non-final state. And when we read the third, it will be in final. For fourth, we will be in non-final. For fifth, we will be in non-final. For sixth, we are in final. Right? So this will give us all the strings over A, which is having a length multiple of 3. What about B? We can have any number of B before A. We can have any number of B's between these two A. We can have any number of B's after 2A. Right? So this will give us all the desired strings in language L. And this is the corresponding table for that. Design minimal DFA for strings over alphabet AB such that number of A in string mode 3 is equal to 1, or we can say that number of A in string W mode 3 congruent to 1. So now here n is equal to 3, k is equal to 1. So there will be 3 states. Okay, there will be 3 states and the qk, that is the here k is equal to 1. So q1 state should be the final state. Thank you. That's it for today folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.